All right, we're gonna look for the amount of gas collected over water. So this is gonna be slightly different because when we're like collecting the gas, when you're decomposing something and collecting that gas, you're gonna have both the pressure of the gas that you're collecting as well as the water vapor. So we need to keep that in mind when we are solving for this. So it says when a sample of KClO3 is partially decomposed in a setup shown in figure 10.15, which if you're looking at your book goes back to page 401. The volume of gas collected is 0.250 liters at 26 degrees C and 765 torr for the total pressure. So how many moles of O2 are collected? We can use the ideal gas equation to get the moles, but our first step is to figure out the partial pressure of oxygen based on that 765 torrs. So we would look in Appendix B in our textbook to find the pressure of water vapor at 26 degrees Celsius. And when you do that, you find that it's 25 torrs. So if you take the 765 torrs minus the 25 torrs from the water, you get a total of 740 torrs. Then I need to convert that torrs into atmospheres by dividing by 760 so that I can plug that into the ideal gas equation and solve for N. So N is going to be P times V divided by R times T. So remember the P is 740 divided by 760. Multiply that by your V, which is 0.250. Divide by the ideal gas constant, so 0.08206. And then multiply that by the temperature. Our temperature was 26 plus 273, giving us a total of 299. And when you do that, I know my picture's in the way, but when you do that, you get 9.92 times 10 to the negative third moles of oxygen. So that's A. How many moles of oxygen are collected? Very few. B, how many grams of KClO3 were decomposed? So if we know how many moles, I should probably go to the next one. If we know how many moles of oxygen we have, we can write a balanced equation. So we're going to take KClO3, decompose it into KCl plus O2. And when you balance that equation, you'll get 2 moles of KClO3 will decompose into 2 moles of KCl plus 3 moles of O2. So we can take our moles of oxygen that we just calculated, which was 9.92 times 10 to the negative 3 moles of oxygen. We use our molar ratios of 3 moles of oxygen to 2 moles of KClO3. So 3 moles oxygen, 2 moles KClO3, because that's what we're looking for, so it goes on top. Oxygen goes on bottom to cancel out with this oxygen. And then this would be canceling out the moles of KClO3. So you get the molar mass of KClO3 on top here. Multiply everything first, then divide, giving us a total of 0.811 grams KClO3. All right. Applying kinetic molecular theory. Oh no, they have a second one. How did I miss that? Oh, that's the practice problem. So here's a practice problem for you if you wanted to. And that's the picture that they were referring to in the previous problem when it says like figure 10.15. So this is a picture. All right, last one here, applying kinetic molecular theory. A sample of O2 gas initially at STP is compressed to a smaller volume at constant temperature. What effect does this change have on the average kinetic energy of the molecules? What effect does it have on their average speed and the number of collisions they make with the container walls per unit time? And lastly, the number of collisions they make with a unit area of container wall per time. Okay, so average kinetic energy of the O2 molecules is determined largely by temperature. So if I compress it, it's not going to really change that kinetic energy. I'd have to increase or decrease temperature to change kinetic energy. So for A, no change. For B, which is what is their average speed, again, because our kinetic energy doesn't change, then the speed isn't going to change. So our kinetic energy, which is A, has no change. Our speed, which is B, has no change. So both A and B are no change. C, is the number of collisions they make with the container walls per unit time. So the number of collisions with the walls per unit time will increase because your molecules are moving now in a smaller space. So think about social distancing. Perfect right now. I have 6 people in a teeny tiny kitchen are going to run into each other a lot more than 6 people in a much larger kitchen. Trust me, I know. And D is the number of collisions they will make with a unit area of container wall per unit time. So this is also going to increase because the total number of collisions with the wall per unit time will increase. So therefore the area per unit time also has to increase. Don't forget to ask questions if you have any.